Hello, this presentation summarizes our preliminary work on improving future time series forecasting using foundation models. Our research explores retrieval augmented forecasting, where we actively search a historical database for the most relevant examples to feed into model's context. Traditional forecasting methods often require a lot of data and don't adapt well to new unseen patterns. A promising new approach is in-context learning, where a pre-trained foundation model learns from just a handful of examples on the fly. But this raises a key question. What are the best examples to show to the model? Should we just use the most recent data, or can we do better? To perform retrieval, we leverage Moment, a powerful time series foundation model. Think of it like a language model, but for time series. It was pre-trained on a massive amount of diverse time series data by learning to reconstruct randomly hidden or masked sections. This training forces the model to understand the deep underlying structure of a series, its trends, seasonality, and core shapes, rather than just superficial values. As a result, Moment can create a compact numerical representation or an embedding for any given subsequence of time series. We use these embeddings to efficiently search for a historical database and retrieve the subsequences with the most similar embeddings, giving us a set of structurally relevant examples for our forecasting task. First, we needed to ensure our retrieval method was reliable. We tested several similarity metrics on synthetic data and found that embeddings from Moment's time series model are highly robust to Gaussian noise, on par with information theoretic and denoising approaches, allowing us to find structurally similar patterns even in the presence of significant noise. Next, we applied this to a real-world dataset using the challenging Ohio T1DM dataset, which contains continuous glucose monitoring data from type 1 diabetes patients. This data is particularly difficult for a prior data fitted network, or PFN, used as a tabular foundation model, because it doesn't follow simple clean patterns. Instead, it's governed by complex hidden biological rules called latent pharmacokinetic priors. This includes things like delayed insulin absorption, how the body processes different meals, and individual metabolic rhythms. Since a PFN is pre-trained on synthetic data, these unique patient-specific biological signals are fundamentally different from what the model has seen before, making it a true test of its adaptability. On this dataset, we used two tabular foundation models, TabPFN and MITRA, and compared two approaches: a baseline method which uses the most recent time steps as in context examples, our retrieval method which uses Moment to find the most similar historical subsequences to use as examples. Key findings and conclusion. Our results confirmed a known limitation to these models. As seen in prior evaluations, for example with TabPFN-TS on GiftEvil, simply adding more examples to the context window actually increased the forecasting error for both methods. And this reinforced the idea that tabular foundation models can struggle to effectively use larger context for this type of task.